Welcome everyone, and thank you for joining us today. I'm excited to introduce our presentation on plant pretreatment processes. The goal of this session is to explore how wastewater treatment plants handle debris and grit to protect their essential equipment. We'll cover the types of debris that enter treatment facilities, the importance of pretreatment steps, and how these processes help maintain smooth and efficient plant operations. Let's get started and see how proper pretreatment keeps our systems running effectively. Now, let's talk about some critical safety considerations to keep in mind. First, slip and fall hazards are a common concern, especially in pretreatment areas where grease, rags, and debris tend to accumulate. These conditions can make the surfaces slippery and increase the risk of injuries, so staying alert and wearing proper footwear is essential. Next, there's the issue of disease exposure. Raw wastewater can contain any number of pathogens present in the contributing population. Tools like bar screen rakes can become contaminated, so it's important to handle them carefully and always practice good hygiene. Speaking of hygiene, personal cleanliness is vital. All operators should always observe good personal hygiene, washing hands thoroughly before eating or smoking. A best practice is to remove work boots and clothing before entering your home, and to wash work clothes separately from your family laundry. By paying attention to these safety points, we protect ourselves and ensure the safety of everyone around us. This fits into the overall theme of maintaining a safe and healthy work environment. Now, let's take a closer look at bar screens, which serve as the first line of defense in wastewater treatment. These screens are typically the very first device that raw wastewater encounters when it enters a treatment plant. They're constructed from materials like stainless steel or aluminum, which are non-corrosive and durable, ensuring they can withstand the harsh environment. The main function of these screens is to trap larger debris, such as rags and coarse materials, while still allowing the water to flow through freely. When the bars are spaced between 3/8 of an inch and 2 inches apart, we call it a bar screen. If the spacing exceeds 2 inches, then it's referred to as a bar rack. Interestingly, bar racks are often installed in bypass channels, especially during maintenance, to divert flow temporarily. Small treatment plants usually rely on manual cleaning, where operators use hand rakes several times a day to remove debris. On the other hand, larger facilities use mechanically cleaned bar screens equipped with traveling rakes that automatically remove debris, often based on timers or control systems. Overall, these devices are crucial because they help protect downstream equipment and processes by removing the larger solids early on. They really form the first essential step in ensuring the efficiency and effectiveness of the entire treatment process. Let's walk through the key steps in the screening's disposal protocol. First, drainage is crucial. We need to allow the screenings to drain back into the influent channel before placing them in containers. This helps prevent excess liquid from accumulating. Next, containment is important. Always store screenings in covered or enclosed containers. This step is essential to prevent flies, birds, and mice from accessing the material, which helps maintain sanitation and safety. Then we have testing. It's important to verify that the screenings pass what's called a paint filter test. This confirms that no liquid is draining from the screenings, ensuring they are properly drained and ready for disposal. Finally, disposal. The screenings should be transported to a sanitary landfill for final disposal. Under no circumstances should we allow drainage into the ground or burial, as that could cause environmental contamination. Connecting all these points, following this protocol helps us manage screenings responsibly, protecting both the environment and public health, and aligns with our overall goal of sustainable wastewater treatment. Now, let's talk about comminutors as a shredding alternative. One of the main advantages is that they eliminate the need to dispose of screenings, which can simplify the process quite a bit. They also reduce manual handling, making the operation safer and less labor-intensive. Plus, comminutors can operate continuously, which helps keep the wastewater treatment process smooth and efficient. However, there are some drawbacks to keep in mind. For one, shredded material can sometimes foul downstream equipment, causing maintenance issues. They also require electrical power to run, which adds to operational costs. And because they handle tough debris, they can be quite maintenance-intensive. What's interesting is that recent innovations have improved this system. Some now combine comminutors with fine mesh bar screens. This combination provides thorough debris removal while overcoming some of the traditional drawbacks, like equipment fouling or incomplete filtering. Overall, comminutors are a valuable option, especially when integrated with new technology, helping us improve wastewater treatment efficiency and reliability. Let's talk about grit removal and why it's so important for protecting our equipment. Grit, which includes sand, sediment, and eggshells, mainly inorganic settleable solids, must be removed early in the treatment process. If we don't remove it, grit can cause serious issues. It wears out pump impellers quickly and deposits in downstream tanks, leading to costly maintenance and potential process disruptions. When grit is allowed to accumulate, it can actually form a cement-like mass combined with grease. This mixture is notorious for being very difficult to remove from pipes and digester bottoms, which can significantly hinder the efficiency of the plant. Now, we also need to consider the amount of grit we expect to remove daily. This is usually measured in cubic feet per million gallons of influent, and it varies depending on the size and age of the collection system. A key point here is the velocity in long-channel grit chambers, which should be around 1 foot per second. This target velocity helps settle the grit effectively while keeping organic solids suspended, ensuring that we remove the inorganics without losing the organics that we want to keep in the process. Once the grit is removed, it's disposed of at sanitary landfills, but only after passing a paint filter test to ensure it's free of contaminants. Finally, there are two main types of facilities that handle grit removal: long-channel grit chambers and aerated grit chambers. Each has its own advantages, but both serve the critical purpose of protecting the downstream equipment and maintaining the overall health of the treatment process. Let's take a closer look at grit removal technologies, which are essential for protecting downstream equipment and preventing buildup issues in wastewater treatment plants. There are two main types we typically use: long-channel grit chambers and aerated grit chambers. Each has its own design principles, operational methods, and maintenance needs, and choosing the right one depends on your plant's specific requirements. Starting with long-channel grit chambers, these are designed to keep a steady water velocity, usually around 1 foot per second or 0.3 meters per second, regardless of flow variations. This steady flow allows heavier inorganic particles like sand, gravel, or eggshells to settle out, while lighter organic solids stay suspended. These chambers often have a parabolic, rectangular, or U-shaped cross-section to help maintain uniform flow, even when flow rates fluctuate. In terms of operation, wastewater flows through the chamber, and the grit settles at the bottom. Mechanical systems, such as chain-end flight collectors, screw conveyors, or clam-shell buckets, are used to continually or periodically remove the grit. The main advantages here are the simple design, low energy use, and robustness, which helps them handle shock loads effectively. However, they do require a larger footprint, and maintaining the optimal velocity can be tricky when flow varies a lot, sometimes leading to organic buildup. This can cause odor issues and raise disposal costs. Regular inspection of the removal mechanisms and periodic cleaning of the channel are essential, and odor control measures might be necessary, especially in warmer weather. Now, turning to aerated grit chambers, these are typically rectangular tanks equipped with air diffusers along one side. The introduction of air creates a spiraling flow pattern, or a helical motion, which helps heavier grit settle while lighter organic particles stay in suspension and are carried out with the flow. When wastewater enters the tank, the aeration generates specific hydraulic conditions. The settled grit collects in the hopper at the bottom and can be removed using airlift pumps, screw conveyors, or other mechanical methods. Plus, the aeration process provides some pre-aeration for the wastewater, which can be beneficial. The advantages of aerated chambers include producing cleaner grit with less organic material, occupying a smaller space compared to long channels, and being less affected by flow variations. They also offer pre-aeration that can help control odors and improve downstream treatment. On the downside, they consume more energy because of the air blowers, have more complex equipment, and can sometimes cause foaming or splashing issues, especially if industrial wastewater is involved. Regular maintenance for aerated chambers involves inspecting and cleaning air diffusers to ensure even air distribution and prevent clogging, maintaining the air blowers and piping, and routinely removing grit from the hopper to prevent compaction. Monitoring foam is also important. In the end, the choice between these two technologies depends on factors like plant size, influent characteristics, available space, and budget. Both are crucial for ensuring the longevity and efficiency of your wastewater treatment system. Let's delve into the fundamentals of flow measurement. At the core, we have the flow formula, which helps us understand how much liquid is moving through a system. The key components here are Q, which represents the quantity or flow rate, A, the cross-sectional area of the pipe or channel, and V, the velocity of the liquid itself. Flow measurement devices are absolutely critical in treatment facilities. They ensure that we can operate these facilities properly and also report accurate discharge volumes to meet permit requirements. Whether it's influent, effluent, or recycle flows at large plants, or just effluent at smaller facilities, measuring flow is essential. Without these measurements, operators wouldn't be able to determine important things like hydraulic loading, organic loading, or the amount of effluent being discharged into receiving waters. It all hinges on knowing two main things: the cross-sectional area and the velocity of the liquid. These measurements form the basis for understanding and managing flows effectively, which is vital for environmental compliance and treatment efficiency. Now, let's take a closer look at some open-channel flow measurement devices. First up are Parshall Flumes. These are constrictions placed within open channels that intentionally cause a measurable head rise. What's great about them is that they are self-cleaning and can handle a wide range of flow variations. They come in sizes ranging from just 1 inch to as large as 50 feet, making them versatile for various applications. Importantly, they require only a small amount of head loss, so they don't significantly disturb the flow. To measure the head rise, we typically use a staff gauge placed about 2/3 up the approach channel, which provides an accurate reading of the flow rate. Next, we have weirs. These are dam-like structures positioned across open channels that also create a head rise. There are different types of weirs: V-notch, rectangular, and trapezoidal, each suited to specific flow conditions. Weirs are especially effective when dealing with effluent flows that contain minimal debris or settleable solids, as these can interfere with accurate measurement. When measuring head rise over a weir, it's important to place staff gauges at least 4 times the maximum head rise away from the overflow point. This ensures accurate readings and reliable flow measurements. Both Parshall flumes and weirs are essential tools in open channel flow measurement, helping us monitor and manage water flow efficiently across various settings. Let's take a closer look at flow measurement in pumping systems. Starting with Venturi and magnetic meters, these are commonly used to measure liquid velocity inside pipes. By combining this velocity measurement with the pipe's diameter and the flow equation, Q equals a times V, we can accurately determine the flow rate. It's important to remember that for these measurements to be accurate, the pipes need to remain constantly full. Next, there's the tank volume method. This approach establishes flow by either filling or emptying a tank of a known volume. By measuring the time it takes to pump that volume, say 1,000 gallons in 10 minutes, we can easily calculate flow in gallons per minute. This method is straightforward and useful for certain applications. Moving on to transmitters and readout devices, primary devices give us instant readings, which are critical for real-time monitoring. For continuous recording or totalizing flows over time, ultrasonic, bubbler, or probe-level detectors are used. These are often paired with chart recorders or electronic totalizers to keep an ongoing record of flow data. Lastly, let's review some common units of measurement. When we're talking about discharge or flow rate, units like millions of gallons per day, gallons per minute, or cubic feet per second are typical. For volume, we often use millions of gallons or acre-feet. Understanding these units helps us interpret data accurately across different systems and applications. All of these measurement techniques and units come together to give us a comprehensive picture of how water moves through our systems, which is essential for effective management and operation.